Our dynamic universe. The key areas covered will be resolving a force into two perpendicular components and forces acting at an angle to the direction of movement. What we will do today is identify how to solve problems when we have two forces acting at different angles, component of forces, and carry out problems on the above. Resolution of a vector. Any vector can be resolved into two components at right angles to each other. We will label our vector x. The horizontal component here would be x with a subscript h, and the vertical component would be x with a subscript v. We've got a little diagram here. We've got an angle on the left. Our vector is x at an angle of theta, and this is equivalent to our horizontal component of x and our vertical component of x at right angles to each other here. We can combine those two diagrams to create a right-angled triangle just here. We've got our x, which is our initial vector. We've got xh along the bottom, our horizontal component, and xv vertically at the side, our vertical component of x. Using trigonometry, SOHCAHTOA, hopefully you remember it, we can figure out what xh is equal to and what xv is equal to. So using SOHCAHTOA here, we can see that sine of theta equals xv over x. I'm just going to do that quickly for you. We've got our hypotenuse here, our opposite and our adjacent, circling the ones we need or have for working out our vertical component. This is going to be this one here, and we need to be using x for this. So O and H, it's definitely sine we want to use, so sine of theta equals opposite over hypotenuse. So sine of theta equals xv over x. That's where this comes from. Rearranging this, we get xv equals x sine theta. Doing a similar method, we get cos theta equals xh over x, so our horizontal component of x is equal to x cos theta. Force. The vertical and horizontal components of a force vector are, respectively, Fv equals F sine theta, where F is our force, and V stands for the vertical component of it, and Fh equals F cos theta. Velocity. We'll talk a little bit more about this later. The vertical and horizontal components of a velocity vector, V, are, respectively, the vertical component of the velocity equals V sine theta, and the horizontal component of the velocity equals V cos theta. Components of forces. In the previous section, a vector was split into horizontal and vertical components. This can obviously apply to a force. We have our force vector there at an angle of theta, and this is equivalent to our vertical component of the force, which is F sine theta, and our horizontal component of the force, which is F cos theta. Remember that the resultant of a number of forces is the single force which has the same effect in both magnitude and direction as the sum of the individual forces. A man pulls a garden roller of mass 100 kilograms with a force of 200 newtons acting at 30 degrees to the horizontal. If there is a frictional force of 100 newtons between the roller and the ground, what is the acceleration of the roller along the ground? Well, first of all, like we've done in the past, let's draw a little free body diagram to help us interpret this question. So we have a roller here. It's at an angle of 30 degrees to the horizontal, so we can put our horizontal in just here, and that's 30 degrees. There is a 200 Newton force here, so we can put this in. And there is a frictional force of 100 newtons between the roller and the ground, so we can add this in, 100 newtons. We want to find out the acceleration of the roller along the ground. We know that we can use our unbalanced force is equal to mass times acceleration to find acceleration, but we don't have our overall unbalanced force. We need to find the horizontal component of this 200 Newton force. So remember, we can make a right angled triangle just here, and we want to find FH just here. Remembering back, FH is equal to F cos of theta, so we can plug these numbers in. We've got 200 times by cos of 30, which is equal to 173.2 newtons. We can now have a look at our unbalanced force. This is going to be equal to our horizontal force take away our frictional force because they're acting in opposite directions. So our unbalanced force is equal to 173.2 minus 100, which is equal to 73.2 newtons. Now we can move on to our final section, which is our unbalanced force is equal to mass times acceleration. So it's 73.2 equals our mass, looking at the question, is 100 kilograms, times by acceleration. Rearranging this, we get acceleration is 73.2 divided by 100, which is equal to 0.732 meters per second squared. An oil rig is pulled by two barges as shown. Each barge applies a force of 10 kilonewtons. What is the resultant force acting on the rig? First of all, let's put some little notes down on our diagram. We can see that if the oil rig is being pulled along, this must be the oil rig just here. And the two barges, one is just here and the other is just here. We can also see that the resultant force is going to be the horizontal component of one of these triangles here. I'll add in some wee lines to show the triangle. We've got our horizontal line along the middle. We can draw a vertical line down here, and so you can see we have, joining them up, a right-angled triangle. Our force is the 10 kilonewtons we've been given. This would be the vertical component of our force, and this would be the horizontal component of our force, making sure that this is a right-angled triangle. We know that our equation for our horizontal component of the force is Fh equals F cos theta, so let's write that in. And we can fill in some numbers here. Fh equals F, our force, that's 10 kilonewtons, so remember kilo is times 10 to the power of 3, multiplied by cos of 30, and that gives us an answer of 8,660 newtons. But this is only the force applied by one barge. For both barges, because they're both at exactly the same angle and applying exactly the same force, all we need to do is multiply that by 2. So 8,660 multiplied by 2 gives us a final answer of 17,300 newtons. A box is pulled along a level bench by a rope held at a constant angle of 40 degrees to the horizontal as shown. A constant force of 100 newtons is applied to the rope. The box moves a distance of 10 meters along the bench, and we want to calculate the work done on the box by the rope. Thinking back to our work done equation, if you can't remember it, you can have a look at your equation sheet. We know that work done is equal to force times distance. From our diagram, we can see that we have the force, that's that 100 newtons just there. We have an angle, but we can't just use the 100 newtons as it is. We have to use the horizontal component of that. So I'll add that in a little diagram just there. Our horizontal component just here, we can add a line down. That would be our vertical component. We know that the horizontal component of the force is Fh equals F cos theta. Adding in some numbers here, we've got 100 multiplied by cos of 40. And that's equal to 76.6 newtons. Now we can work out the work done, which is the force multiplied by the distance. So we're doing 76.6, which is what we just worked out, multiplied by the distance. That's given in the question just there. That's 10 meters. So our final answer is going to be 766 joules, because remember, work done is energy. So our final answer there is C. A box of weight 120 newtons is placed on a smooth horizontal surface. A force of 20 newtons is applied to the box as shown. The box is pulled a distance of 50 meters along the surface. We want to calculate the work done in pulling the box. So this is very similar to the last question, so we can use our work done equation again. W equals Fd. And we have our force at an angle just here. So we want to be calculating the horizontal component of the force, this Fh just here. So Fh equals F cos theta, which is equal to 20 multiplied by cos of 30, which is equal to 17.3 newtons. We can plug this into our work done equation. So we've got 17.3 multiplied by the distance, which is, we can see in the question just there, that's 50 meters. And this gives us a final answer of 866 joules, which is answer B. A box of mass 18 kilograms is at rest on a horizontal frictionless surface. A force of 4 newtons is applied to the box at an angle of 26 degrees to the horizontal. Part 1. Show that the horizontal component of this force is 3.6 newtons. Let's take that by itself first. So, part 1, we're showing the horizontal component of the force. So, FH just here. And we know the equation for this, FH equals F cos theta. Should know it off by heart by now. And that's equal to 4 times cos of 26 degrees, and this is equal to 3.6 newtons. Exactly what they were intending for you to find out in the question. Show that it is 3.6 newtons. Let's look at part 2. Calculate the acceleration of the box along the horizontal surface. So we already know that the horizontal component of the force is 3.6 newtons, and to calculate the acceleration, we want to be using the equation our unbalanced force equals mass times acceleration. It's a frictionless surface, so our unbalanced force is going to be equal to our horizontal component of the force. We haven't got any friction acting against it. Therefore, FH equals MA. We can start plugging in some numbers. 3.6 equals, where's our mass in the question? There we go, 18 kilograms just there. Times by our acceleration, rearrange this. We've got 3.6 divided by 18, which gives us an answer of 0.2 meters per second squared. Part 3. Calculate the horizontal distance travelled by the box in a time of 7 seconds. We want to use our equations of motion for this. So again, it's horizontal, so we want to calculate the horizontal distance, writing down suvat, so our displacement, that's what we would want to know. Our initial velocity, having a look at the question, the box is at rest on a horizontal frictionless surface. So that means our initial velocity is going to be 0. We don't know what our final velocity is. Our acceleration we worked out in part 2, that's 0.2 meters per second squared. And our time is given in the question just here, that is 7 seconds. So if we want to work out displacements, but we don't have our final velocity, we want to be using the equation S equals ut plus a half at squared. And let's pop our numbers in. S equals 0 times 7 plus a half times 0.2 times by 7 squared. Popping that all into the calculator, we get a final answer of 4.9 meters. Part B. The box is replaced at rest at its starting position. The force of 4 newtons is now applied to the box at an angle of less than 26 degrees to the horizontal. The force is applied for a time of 7 seconds, the same as before. How does the distance travelled by the box compare with your answer to part 3? You must justify your answer. Okay, so if we need to justify our answer, we want to be writing a couple of little bullet points or sentences, and let's think about how to answer this question. If our angle has changed, this is going to affect the first equation that we used, our horizontal component of the force being equal to F cos of theta. When theta decreases, cos of theta is going to increase. That's just the way our cosine function works. You can try it in a calculator if you want, but it will show you that by decreasing theta, your total cos theta is going to increase. So if the right-hand side of our equation is increasing, because remember this F is not changing, this F just here, that's not changing, therefore our horizontal component of the force is going to increase. So that can be our first bullet point. And if the horizontal component of the force increases, remembering to the second equation we use, which was our unbalanced force was equal to ma, which remember this was equal to our horizontal component of the force. If that is increasing, then our left-hand side of the equation is going to increase just there. The mass stays the same, so that means the acceleration must increase. So that can be our second bullet point. And finally, think back to the third equation that we used, our equation of motion. We used S equals ut plus a half at squared. Remembering this first section, this was just equal 0. It's starting at rest again, so we can ignore that. Our time is staying exactly the same because we've got 7 seconds like before. So we can ignore our time. That means if this acceleration increases, I'll do that in green instead. If this acceleration increases, then that means our displacement is going to increase. So that can be our third little bullet point there. The distance traveled or the displacement increases. And that'd be our final answer there.